Hello everyone and welcome back to the channel. Today we will continue with the solar panel fault diagnosis project. As seen in the previous video, we have created the data set. Then we did some visualization on that particular data set using principal component analysis. In this uh, in this video, we are going to do model training using the data set that we have created. But one important thing to note here is we have created two sets, one for limited power and one for maximum power. In this example, we are going to analyze them separately. That means one dataset will only have limited power and another dataset will only have maximum power. So the first task is to import the necessary library. Everything is same. These are our model that we are going to train today. We are using SLN library for that. And to validate the model's accuracy, we'll do cross validation. Cross validation as in yeah that to validate any model's performance, we are going to do cross validation. For that, we imported from model selection this. These are the matrices we are going to use, and this is the standard scaler for scaling of the data. The first thing we are going to do is import the limited power dataset. So if I run it, this is the dataset, and it has total 7 type of faults, but the entire dataset is based on limited power mode. And we have similarly another dataset which is based on maximum power mode. The next step will divide it into train and test split, then do the standard scaling. So this is what it is about. As I already explained that I'm not taking time as one of my input features in the last video. So I'll take the data frame. I'll take from the number one, the index, the one first column up to the penultimate column up to BF. This will be my feature, and the last one, that is label, will be my target variable. I'll use the train test split function to divide my dataset, divide my input and output features, their 20% test size. So this is what my X train, this is my Y train, X test, Y test. If I just give a random value, here you can see this is my X train. And as I keep shuffle equal to true, all the indices are shuffled. So in the next step, I'm going to scale my data. And the reason I'm scaling, I'm doing the standard scaling is I can show you here. Yeah. Okay. So here, as you can see, we have different features. Here x1, x2, and x3 are different features, just like here. This IPV, PPV, these are my features. You can clearly see that IPV has a range of around 1 to 2, but where PV has a range compared to 100, and they have all the features have different ranges, as you can see here as well. So initially x1, x2, x3 had very different ranges, but after doing the standard scaling, they become something like this here. So what this happens, why we are doing this is many algorithms that are based on finding the minima or or finding the global minima of a loss function. They use the assumption that it is based on a standard normal distribution. In that way, they reach their global minima fast. This is one reason we are doing the standard scale. Okay, that was about it. Doing the standard scaling. Yeah, this is the standard scaling. After doing the standard scaling, this is how the features look like. You can see that all the features are in almost similar range, more or less 0 to 1, little more than 0 to 1. It basically has mean of 0 and a standard deviation of 1. Yeah. As you can see, it has a mean of 0 and standard deviation of 1. So this process, this dividing into dataset and then doing test and train split, I'm going to cut everything and write a function for that. So what it will do, it will first get the data frame, convert it into my feature and target, then do a train test split on that. And once I get my train and test data, then I'll use the standard scaler to fit and transform on the training data. And the fitted scalar method, I'm again used to transform the test set. One thing to remember here is I'm not again transforming my scalar on the test set, because whatever the value of mean or sigma are there in the training set, they are getting fitted into the scalar value. That is one thing. So I'll run this one. Okay. To see the example, this is what I'm doing here. This is my function that I created, split transform. I'll input the data frame and giving a split ratio. Suppose I keep my split ratio equal to 0.2. Yeah. So the number of samples in the training set is 8,700 and in the test set is 2,100. Something like that I can do. Right now I'm keeping it very less because I'm going to use this XC train. That means standard scaled training data to fit a machine learning algorithm using cross validation. And we're going to do that in model training. So let me tell you what is cross validation. This is a random photo that I get from the internet, and you can see that this is what basically cross validation is about. When you basically take the data and you split it into a training set and a test set by randomly shuffling it. Suppose this time, if you have k-fold cross validation, and if k equal to 5, then you will divide the entire data set into 5 parts. First 4 will be your training, and next will be your test set. You use the training set to train your model and evaluates the model performance on the test set. So in that way, suppose you got error. In this case, it is saying error, but let's say I get accuracy of 90%. In the next case, I'll use this the blue one, the data marked in blue to train my model, and the gray one to test my model. So in that way, I'm getting a different error or accuracy. So that will be accuracy too. Similarly, I'll take different samples for one for training, one for test, and then average them out to get my to get my final error or accuracy value. So that is what k-fold cross validation does. It is a better method. It is a much better method as compared to taking only one test set and one training set, because then some biases may be included in that particular one. So that's why in this project we are going with the cross validation. Okay, so to generate the shuffling, I'm doing n splits equal to 5. That means I'm going to repeat this case for 5 times. I want to do it 5 times. So that's what it means. N split equal to 5 and test size equal to 0.3. That means this test set for each iteration will be 30% of the data, and 70% will be my training, 30% will be my testing. That's what it means. If I just iterate through for train index and text index in this object CV dot split, I'm using exceed train, and I'm printing the indexes of the training and test set. Then you can see that this is my the indexes like these values, these indexes for the training one and for the test one. This is as I have kept n equal to 5, I'm getting 5 iteration, and each iteration I'm getting 30% for the test set and 70% for the training set. Once I get this data and it is shaped in the CV, I'll initialize a classifier. Suppose first is I'm using a random forest classifier. I'm not doing any hyperparameter tuning for now, and I use the cross validation score function. And here the first one is my model, the CLF or the random classifier that I have already initialized. Then I give the features, then the target, and CV. The cross validation is CV is the one that I initialized here. It will shuffle the data and generate a shuffle split. This basically indexes data is saved in here. And n jobs minus 1, that means all my cores will be utilized for this. Once I do this, now if I print, so okay, this is my score. So basically what it did, for the first split, this is my score. For the next split, this is my score, and so on and so on. You can see that we're consistently getting accuracy above 97%, which is very good for this model. And again, I don't want to repeat this task again and again for every model I'm going to train. So I'm just going to delete this one and just make a function out of it. In the first case, I'm going to split the data and transform, like the scale it. I'm taking the data frame as an input and directly going to scale it. Once the data is scaled, I'll generate a shuffle split. Whatever the k-fold will be, that will be one of my input to the function. CLF is a model that I need to initialize before this function. Scores will basically give all the scores generated through the cross validation. I'm printing the score. And also I'm doing one thing, I'm printing the mean score and the standard deviation of the score so that I can see that how accurate my model is. I'll run this one. Next, I'll do the same testing for the random forest classifier, which we already see. We don't need to understand this again. This function I'm using model with cross validation. Model first will be my data frame, first input, then my classifier that I have initialized here. K-fold I'm taking to be 5 because it takes a lot of processing, and I'm taking test size to be 30%. I run this. Yeah. So finally it says that this is the total output I got, and it says that my accuracy of the model is 97.78% with the standard deviation of this much. If the standard deviation would have been high, that means that our model is not working good. It has some uncertainty involved. But here the standard deviation is way too low. It is 0.25%. So you can say it's a good model. Coming to decision tree, now instead of just what we have to do, we have to initialize the decision tree for this name and repeat the thing. See, the k-fold like the number of splits, the number of iteration for the cross validation, just as I'm taking. I perform this. Then yeah, here the accuracy is less because you know that the decision tree, the depth is very high, and it is only one decision tree is there, so there is high chance of overfitting on a training data. That's why probably we are getting a lesser accuracy and little more standard deviation as well. Then next we'll try SVM. For the SVM also we are getting 94% accuracy. Next we'll try KNN. For the KNN, the accuracy is also very good. It's about 95%. For logistic regression, regression is not able to perform that good. It is only 68%. This may be the case because logistic regression is a linear algorithm, and as our data we see in the previous video that it's not linearly separable. Maybe that's why logistic regression is not able to perform that good. SVM is also a linear algorithm, but it applies the kernel estimations. It applies RBM kernel in this case when there is default. Default is the RBM kernel. So using that kernel, it is able to get some non-linearity, and that's why it is performing very well. Finally, is our 9 bias classifier. That is also 76%, not that one. So finally, we can say that our random forest is performing very good. Next, we can go ahead and try to do some hyperparameter tuning of the random forest in order to maybe we can increase up 99 or 100% of the 100% accuracy. If I just see the confusion matrix here, what will I do? I'll use the split transform here. I'll initialize the random model classifier, train the random model classifier, then use the confusion matrix display method from scikit-learn. First will be my model. Next will be my input feature, the test data. This is the input feature for the test data, the label for the test data, and the classes I am using is model classes. Or let's see, I'll show you what are the model classes. These are basically my fault name, the name of the fault that I use. Okay, I just run this one using the random forest algorithm. You can see that the performance is very good. Like most of the things are on in here, and also, yeah, one thing you can see here is there are 8 misclassification for the like a predicted label is normal state, but it has some fault. The true label is actual, that means it has some fault, but our model is predicting it to be good state. This is a problematic case because this may lead to accidents or hazardous, or may lead to some kind of hazard. In this array, we don't need any misclassification because in that, if there would have been any misclassification, that means there is some fault, but our model is not able to predict that fault, which is very dangerous. So yeah, that is it about for the intermediate power mode. Next, what are we going to do in this video only? Well, we're going to use the maximum power. Everything is same. We're going to use the same library. Just the difference is here. Here, when I'm importing the data frame, I'm using the maximum mode, the data that I created for the maximum power mode. Let's run it. Then the function is same, split transform, to split and transform the dataset. Then for the model training, I'll use the same function that I used previously, and I'll try to train a random forest algorithm initially first. Okay, so here the random forest is performing even better. It's like 99% accuracy, and even variance is also good. Let's see how decision tree performs. Yeah, decision tree has also better accuracy. So every model seems to have a better accuracy as compared to the previous set in the intermediate power. Let's see, this is 90% good. Logistic regression, it has also very good accuracy as compared to the other data set. It has 76%. Good prediction. So if we see the confusion matrix here, using the best predictor, that is the random forest, here you can see we have 3 misclassification. For if there is a fault, but our model is not able to identify, and which was 8 in the previous case. So, so there is one observation we took from here, that random forest is best classifier among everyone for this particular data set. Just now we have seen the performance of various models, once on the limited power dataset and once on the maximum power dataset. Now we are going to combine both. So let me show you how we are going to combine both. Alright, as you can see in this presentation, this is my limited power dataset, and this is my maximum power dataset. So what am I going to do is I'm going to just stack one over another. So whatever my limited power data set is there, I'll just put it there. Then I'm just going to concatenate them row wise, and now I'm entering my new data frame, which will have now total 16, which will have now total 16 number of class labels. So 8 for the first one and 8 for the second one. Alright, and then we are going to apply the same kind of machine learning models and see the performance, whether the performance increases, decreases, and we'll see that. So initially we'll just import all the dataset. Next, I'm going to import both the dataset. One is maximum power, one is limited power. Then I'm going to stack them one over another using pd.concatenate, where I'm just ignoring the accesses and access is 0 rows. So if I see my dataset now this is what it looks like. So it has total 21,000 rows. That's it. If I see total label, like what are the different classes available in my dataset, then I can see this. Total 16 different labels are here right now. Now what I'm going to do, I'm going to divide the dataset into train, SP, as I did in the previous cases. Okay, so okay. Now with this function, I'm going to do the model training, just like the previous one. And I'm using that. Just initially, I'm just starting with the random forest, and I have total 21,000. I'm using test size 30, but this is for the different one. This one it shows for this particular one. Test which I have kept here 0.01. So please ignore this one. This is not the actual amount of data set for the training. That is this test size is defined here. Alright. So you can see that it is getting 98% accuracy, not bad. For the maximum power mode, it was getting 99%, and for the intermediate power mode, it was getting something like 97. So it is in between both of them. So not bad. We can just concatenate instead of training two different algorithms. You can just train one algorithm on the entire dataset, and it will also become a satisfactory result. Let's see what is for the decision tree. Yeah, it is 96% for the SVM. Let's do some sketches. Yeah, for the SVM, we are getting 94%. For the KNN, we are getting 95%. For the logistic regression, we are getting 74%. So it's actually not that good, but the rest of the algorithm are performing pretty well. And among all them, the random forest is performing the best with 98% accuracy. Same thing we do to see the number of misclassification here. To see the number of misclassifications, yeah, here I can see predicted label F0L. In F0L level, I have 12 misclassification, and for F0M, I have total 2, 4, 1, 5 misclassification. So total 12 plus 5, I have 17 misclassification in this using both the data, using both the classes of data. That was one case. In the next step, what I'm going to do is I'm going to reduce the number of labels. So initially what we had, now if we just tag both the dataset one over another, we will have total 14 features, one for the low, same fault for the low, same fault for the medium, low, medium. Okay, so in the next step, I'm going to remove that. So I just have the 7th fault. I'm not going to consider whether it is maximum power mode or the lower power, or the low power, intermediate power. So that's what I'm going to do right now. Same, I just imported both the dataset, and okay, so this is my data frame. So what am I going to do? I'm going to see data frames label column, and I'm just going to take the first one. I'm going to convert this F0M into just F0. I want to omit this string M. So I'll just have the fault F0, F1, F2, F3, F4. So this is the first line I did, and yeah, I'm going to take a temporary variable called class. Save this F0M value in a class. Then what am I going to do? I'm going to take all the elements up to the last one. That means I'm just going to ignore the last one. So now my class becomes F0. And now I'm going to assign my data frame the last one. Okay. Okay. So now if I see my df, this is how it looks here. So see, So now for the first index, I have 0 because I did it for the first index. So for the first index, I get rid of. I want to do the same for the entire data set. So what I'm going to do, just going to write a for loop for up to length of df1. This is my df1. I'm going to iterate through each row, run the same thing, and that's how I'm going to iterate one row one by one, each row one by one. And I'm going to do the same for the df2 as well. My data frame 2, I'm going to do the same thing for the data frame 2 as well. And so I don't need this. Yep. I'm going to do the same thing for data frame 1 and data frame 2, just taking out all the nodes. And then I'm going to concatenate them one over another. Okay, so now this is how my data frame looks like. Now I have label f0, f0, f0. And if I just see label.unique, then I have only 7 labels. There are no modes are considered in this, like the fault in the fault type. The modes are not considered. I have just straight f0 is normal, f1 is different type of fault, f2, f3, there are certain type of faults. So what am I going to do? Now I'm going to see different models and their performance on this particular data set, where I'm only considering 7 types of fault. So yeah, that's it. So this is what I'm doing. I'm initializing the model, then using my model cross validation function, I'm going to validate using cross validation with 5-fold and SS 30%. To do that sum for all type of algorithm, it will take some time. Started already. So for the random forest, we'll see now. Yeah, for the random forest, we're still getting 98% accuracy, so which is a good thing. You don't have to consider the modes in the fault when you're taking 7 faults. I was hoping that maybe the accuracy will increase, and the number of labels are less, so it has less of the field to play with or less of the field to decide from. So I thought maybe the accuracy will increase, but no, it's not increasing. Okay, so the accuracy is more or less same for the random forest value 98%, for the BCMT 96, which is just the same with 14 type of fault. Okay, so that's what we saw right now. Next, what I'm going to do, I'm going to introduce the modes HF as a feature and see if there is any difference there. So what I'm going to do, this is df1.insert. It will insert at the first column position a new column called mode, and it has all the values of 0. As I want to convert it to a categorical one, so 0 will represent maximum power mode and 1 will represent limited power mode, because my df2 is limited power mode and df1 is maximum power mode. So yeah, I'll just show you much better. Yeah. So now see, another extra feature is added to my dataset where the mode is there, and if I just say mode has two unique values, 0 and 1, 0 for the maximum power value and 1 for the limited power. So that information I already encoded as a feature, and now I want to see if there is any performance difference by using some extra feature like limited power mode or maximum power mode. I'm going to do the same thing only. Yeah, not really. It's still now also getting 98% accuracy, 96% on the decision tree on the support vector machines. Okay. So after running the entire code on this dataset, where we have more information, the operating mode information, the accuracy is not increasing. So finally, we can conclude that our initial uh, method was the best, because we don't need to take care about adding a new feature. We can just use this data given here to finally predict the label of the all the 16 labels, 8 for the maximum power mode and 8 for the limited power mode, which is very advantageous. All right. So this was all about model training and testing dataset. Model training and testing on the solar on the solar panel dataset. We are able to get about 98% accuracy, about 98% accuracy using random forest on this dataset, and maybe some hyperparameter tuning of random forest may let us increase this accuracy even further. Alright, so in the next videos, we are going to see deep learning methods for the same problem, and we are going to see if the performance we can increase this performance, or maybe it's not possible to increase. That we'll see in the next class. Okay, bye.